The first challenge in creating artificial magnetic fields for habitats is understanding that a magnetic shield is not simply a technological accessory. It is an attempt to recreate one of the most important planetary defense systems in nature. Earth's magnetic field is generated deep beneath the crust by turbulent flows of molten iron, creating an invisible cocoon that stretches far into space and deflects dangerous charged particles from the sun and beyond. Without it, radiation would gradually erode the atmosphere and expose life to a constant storm of energetic particles. Any artificial habitat on the Moon, Mars, or in deep space must somehow replicate at least part of this protection, but doing so at a human scale introduces enormous engineering difficulties. The most immediate issue is power. Magnetic fields strong enough to meaningfully deflect charged radiation require immense electrical currents. On Earth, planetary magnetism is sustained by the energy of an entire world-sized dynamo operating continuously over geological timescales. In a habitat, engineers must produce a stable field using compact systems with limited resources. Traditional electromagnets consume huge amounts of electricity and generate heat that must be dissipated. In space, thermal management becomes a major obstacle because heat cannot simply escape through air. It must be radiated away slowly, demanding large cooling systems and careful energy budgeting. Superconductors are often proposed as the most realistic solution because they can carry massive electrical currents with minimal resistance. However, superconductors create a different set of challenges. Most require extremely low temperatures to function properly, meaning habitats must maintain cryogenic systems in environments already struggling with harsh temperature extremes. A single failure in cooling could cause the superconducting magnet to quench, rapidly releasing stored energy and potentially damaging critical infrastructure. Designing reliable redundancy becomes essential, especially for habitats located millions of kilometers from Earth where emergency repairs are impossible. Field geometry is another underestimated problem. A magnetic field is not a rigid wall. Charged particles move along magnetic lines in complex spirals and trajectories. If the field is poorly shaped, radiation can become concentrated in certain regions instead of being deflected. Earth itself demonstrates this phenomenon through the Van Allen radiation belts, where charged particles become trapped by the planet's magnetosphere. Artificial systems could accidentally create similar high radiation zones inside or near the habitat if engineers do not carefully model particle behavior. This means habitat shielding is not just about producing magnetism, but about sculpting magnetic topology with precision. Scale also matters enormously. A small magnetic field around an astronaut's room would offer little practical protection because high-energy cosmic rays possess tremendous momentum. To effectively deflect them, the field may need to extend far beyond the structure itself, creating a protective bubble rather than a thin barrier. The larger the protected volume, the larger the magnet system required. This rapidly increases structural mass, power demand, and engineering complexity. Every kilogram launched into space remains expensive and difficult to transport, forcing designers into constant trade-offs between safety and practicality. One promising strategy involves combining magnetic shielding with traditional physical shielding instead of relying on magnetism alone. Water, polyethylene, and lunar regolith are all effective at absorbing certain forms of radiation. A habitat could use thick physical walls to block lower energy particles while magnetic systems reduce exposure from solar storms and charged plasma events. This layered approach mirrors how Earth protects life through both atmosphere and magnetosphere working together. Practical habitat design often succeeds not by finding one perfect solution, but by combining multiple partial solutions into an integrated defense system. Artificial magnetic fields also create biological and operational concerns. Strong magnetic environments can interfere with sensitive electronics, navigation systems, medical equipment, and communication networks. Human biology itself remains an area of active research. While humans live comfortably within Earth's magnetic field, exposure to stronger or highly variable artificial fields over long durations is not yet fully understood. Engineers must balance shielding effectiveness with long-term physiological safety, particularly in habitats meant for permanent settlement. Deep space habitats face an even greater challenge because they cannot rely on any planetary assistance. Unlike Mars, which possesses limited crustal magnetic remnants, or the Moon, where habitats could be buried underground for protection. Spacecraft traveling between planets are fully exposed to galactic cosmic radiation. These particles carry such extreme energies that even powerful magnetic systems may struggle to stop them completely. Some concepts propose plasma shields, where magnetic fields trap ionized gas around a spacecraft to mimic miniature magnetospheres. Others explore rotating superconducting rings or hybrid electrostatic systems. Each idea offers promise, but each introduces difficult questions about stability, maintenance, and energy efficiency. Long-duration reliability may ultimately become the defining issue. A habitat's magnetic shield cannot function like experimental laboratory equipment requiring constant adjustment by specialists. It must operate continuously for years with minimal maintenance, surviving micrometeoroid impacts, radiation degradation, thermal cycling, and mechanical stress. Every component must be designed with extraordinary resilience because failure could expose inhabitants to lethal radiation doses during solar particle events. In practical terms, artificial magnetospheres are not merely scientific devices. They are life support systems as fundamental as oxygen or water recycling. The challenge becomes even more profound when considering planetary scale applications. Some researchers have proposed generating large magnetic shields for Mars itself, perhaps by placing massive magnetic generators in orbit or near stable gravitational points in space. The goal would be to partially restore atmospheric retention and create safer conditions for future colonization. While theoretically intriguing, such projects demand technological capabilities far beyond anything humanity currently possesses. The required infrastructure, materials, and energy production would rival the scale of entire civilizations.